Yes, I am Rajesh. In the last tutorial, we have seen something about memory operations, memory read, memory write operations using loading and storing instructions. In this tutorial, we are now going to see about GPIO programming, the general purpose input output programming. In microcontrollers, to use a port as an input or output, first of all, the port has to be programmed as an input or output port, and then data is to be sent or received depending on the functionality of the port. In our microcontroller, there are 5 ports, port A, B, C, D, E for this KL25Z microcontroller development board, and all these ports are of 32-bit in length, and each port pin can be configured as an GPIO pin or analog pin or some other functionality depending on the chip. Now we are going to see about how to program these GPIO pins in KL25Z ARM microcontroller development board. Before going to this GPIO programming, we are going to see some registers, and these are the steps to be taken care of while using a port as an output port. First of all, the initialization of SCGC5 is to be done, and then the initialization of port control registers is to be done, and data direction registers are to be initialized, and later we are going to use this set register or clear register or toggle register to set or clear or toggle the corresponding port pins. This SCGC5 register will make the clock enable for the respective ports, whereas this port control registers will enable the GPIO functionality of respective port pin, and this data direction register will make the port as an input or output port, and these are going to be used for manipulating data on the port register. Now we are going to see these registers one by one. In brief, to see all these registers, we are supposed to have this document KL25 subfamily reference manual. Now we are going to see about SCGC5 first, and this will be in the system integration module. In the system integration module, we can find a number of registers: system option register, configuration option register 1, 2, 4, 5, 7. So there are many number of registers in this one. We are going to take care on SCGC5 register. As you can see, this SCGC5 register is actual of 32-bit capacity, in which only 7 bits are of use and the rest of the bits are reserved under red dash zeros or 1 depending on the pins. So these pins will read as 0, and these bits read as 0, these bits read as 1, and these bits read as 0, and these can be programmed by the user. Now we are going to see the functionalities of port A and port E, 9, 10, 11, 12, 13 bits. As we can see, for port A or port D or port C or port B, for all the ports, if it is a 0, then the clock is disabled on that particular port. If it is written 1, then the clock is enabled on that particular port. Unlike other microcontrollers, we need to enable the clock in this ARM microcontroller development board for the port to be used as an input or output port. And then we are going to see about port control register, and we can see here there are pin control registers for port A PCR0, pin control register N port A PCR1. As such, there are 32 pins for port A, and there are 32 registers for port A with the name pin control register. And with this register, each pin of the port A can be controlled as a GPIO pin or not. In the same way, port B has got 32 PCRs, and port C, port D, port E has also got each 32 pin control registers. Apart from these registers, we are having 2 registers: global pin control low register, global pin control high register, and apart from this, interrupt status flag register to show the status of interrupt on each port pin. And this global pin control low register, global pin control high register are used to program all these 31 registers at once. If you are not able to do all the 31 register initialization individually, we can use this low register or high register to program many of the registers at once. Now we are going to say about pin control register, and this pin control register is of 32-bit capacity, in which most of the bits are reserved and are read as 0 by default. Now we are going to see about the mux bit in the pin control register. ISF interrupt status flag is not required. As of now we are not caring about this interrupts. So interrupt configuration not required. Mux, pin mux control. In this pin mux control, if you write 000, then the pin will be disabled. If you write 001, then it will be acting as alternative one, that is called GPIO. So if you write 001 in this position, then that particular port pin can be used as an input or output for general program, and these are not required as of now. This passive filter enable is used whenever the port pin is configured as an input. Now after this pin control register, we are going to see about data direction registers, and this data direction registers will be in the category general purpose input output register. And we can see this GPIO memory map. Each port has these registers: port data output register, port set output register, port clear output register, port toggle output register, data input, data direction, data output. And for port B, similarly all these registers will be there. This data output register will define the data to be at the output of the port. That means if you are sending some 20H, that 20H is stored at this data output register, that is being at the output of the register. Then port set output register. If you want to set a particular pin of port A, then we are going to use this port set output register. If you are going to clear some particular pin, then we can use clear output register. If you want to toggle a particular pin on the port, then we can use this toggle register. And this data input register will read the data present on the port pin if it is programmed as a input port. And this data direction register defines whether the port is going to be used as an output or input, and individual port pins can be programmed as input or output. And similarly for port B, port C, D, E, all these registers are applicable. And one thing we can notice here is each and every register is having a unique address location. For port A data output register, PDOR 400F F000 is the address location. If we want to write something to this register, first of all we have to load this memory address into some register, and we have to use the store instruction to write that particular data into this location. This is nothing but memory addressing, loading and storing. Loading this address into some register, storing some value at this register using LDR and STR instructions. Now we are going to see about this GPIO programming. Prior to the GPIO programming, we are going to concentrate on LED blinking. We all know that this Freedom board has got 3 LEDs. One LED is at PTB 18, another LED is at PTB 19, another LED is at PTD 1. So we have port B 18th pin and port B 19th pin for LED red and green, and port D first pin is for blue LED. Now we are going to program this port B and port D in such a way that these LEDs are going to be blinked, and we are going to program port B 18th pin and port B 19th pin as output and port D first pin as output. Nevertheless, rest of the pins can be made output or input, but these pins must be made as output to use the LEDs. Now we are going to look at a simple program which are used to control the LEDs. I have already written a program, we can see here, and I have taken all the address registers PB, PDOR. I have given the names PD, PDOR, PB, PSOR. For my convenience, I have taken PB as port B and these registers as the particular register. Now we are going to see about these LEDs. LED 1 is connected to port B 18th pin, LED 2 is connected to port B 19th pin. So port B 18th pin will have one pin control register, port B 19 will have one pin control register. These are to be programmed, and then pin control register for port D1 is also to be programmed. Prior to that, we have to program the SCGC5 register. That is the sequence of steps you are going to follow now. And now I have taken all the addresses PDOR, PSOR, PTOR, PCOR, PDDR, PCR18 and PCR19 SCGC5. Similarly for port D also I have taken all the registers required, and I have defined some data which are above the decimal value 255 that cannot be loaded into the register directly. Now we are going to see the first line of the program. R0 is equal to SCGC5, R1 is equal to data 1. Data 1 is 1580. SCGC5 is loaded with the value 1580. If we go through the SCGC5 register, so it is here 1580. 1580 can be written as 0001, 0101, 1000, rest all zeros. That means here, from here, if we see, the 15th bit is 0, 14th bit is 0, 13th bit is 0, 12th bit is 1. 12th bit is 1 in the sense we are making port D bit as 1, and 5, 0, 1, 0, 1. So that is port B pin is made 1 and rest all are zeros, and these are 1. Writing a 1 to it or 0 to it does not matter anything. This will be as default by 1, and rest all are zeros here. So we have written 1580 so that port D and port B are programmed as to enable the clock for the particular ports. Port B and port D is enabled with these clocks. The next one is PCR18 data 2. We are loading data 2 is equal to 100H for this PCR18 and PCR19. As we can see, here R1 is having the data 2 only, that is being stored at this location 2. So PCR is equal to 100. If we go through this PCR register now, we can see 0, 0, 1. 100 in the sense last two nibbles are 0. So this is 0 and this is 0, this is 1. 0, 0, 1, we are writing 0, 0, 1 to the mux bits so that it is used as GPIO port pin. And then we are going to use this PDDR for port B. PDDR for port B in the sense port data direction register for port B, and we are loading data 4 at that address location. Data 4 is all F's. Writing all F's will make all the port pins as output pin. Writing all zeros will make all the port pins to act as input pins. If you write the respective ones will act as output port, the respective zeros will act as the input pins. After that, I have written this PSOR, port set output register for port B. I am writing data 3 and data 6. I will show the significance of this while programming, while debugging the program. So PSOR is having the address of this one, and I am writing data 3 and data 6 at two different instances. Data 3 is having 8000 and data 6 is having 4000. So 8000 in the sense the 19th bit is made 1 and here the 18th bit is made 1. 19th bit for LED 2 and 18th bit for LED 1. You can see here this is 19th bit, 18th bit. I am making 1 at this at once and 18 at once. At two different instances I am making this one. And I am loading the PCR1 of PD register, and The same data 100H I am going to store at this memory location, and PDOR is loaded with 02. This is port data output register. Before programming the port as an input or output port, we can write the data to be present on that port by default with the help of this port data output register, which I haven't used for this port B. I will show the difference while debugging this program. Now after loading this PDOR, I am going to load PDDR with data 4. So data 4 is all F's. In this case also I am making all the pins of port B to be output and controlling the LEDs. To control the LEDs, we are going to use this port control output register or port set output register or port toggle output register. In this case, as LEDs are connected to common cathode, that means the LEDs are connected to the port pins with the anodes of the LEDs grounded and the cathodes are connected to the port pins. That means if you write a 0 on the port pin, LED is going to be lit. If you write 1 on the port pin, LED is going to be off. That's why we are using this port clear output register to clear the particular bits on the port so that the LED can be lit. Similarly for port B also the same. Now we are going to compile our program. We are going to debug this program in software so that we can see how the registers are getting changed. This has been disabled. Now we are going directly to our first instruction. Now SCGC5 R0 is loaded with SCGC5 address, R1 is loaded with 1580 value, and we are getting an error 65 access violation at this address location, no write permission, because we are not using the board and these memory locations need to have some permission to write or read from the memory locations. For that we are going to see something. We have to go to debug memory map. You can see here these are the permissions on the particular memory locations wherein we are not having this memory location 40048038. If we want to add this memory location to this range, we can write here 0x40, 0x4 5000000. I am selecting from 4000 to 5000 so that all these registers get covered in this memory range. I am giving it a read permission as well as write permission and map range so that it will show that map size truncated to 128 MB. So it has been such that 4000 to 47FFFF. In this range we are getting covered all these special registers. Now we can close this and we can see for this thing we are not going to get that error. Now it is loading the PCR18 register address 100, and you can see we have not got any error such as no write permission or no read permission like that. And to view these registers whether they are getting changed or not, we are going to see the register contents. To see that register we are going to see this one, system viewer windows. In this one we are going to port. So in this port we are going to have all these registers as we can see here, PCR0, PCR1, PCR2, PCR9, 10 up to PCR31, and you can see here PCR18 is loaded with 0x100 and PCR19. Now we are going to load this PCR19. So PCR19 is loaded with 100 and then PDDR. For getting the PDDR we are going to see for GPIO port B. PDDR is 000 initially. So it is all Fs. This will make all the port pins to act as output. And PSOR, we can see the PDPCR1 from here, port D. PCR1 is written with 1000, and we can also view the GPIO port D. So PDOR is written with 0002. Now PDDR. So PDDR is written with all Fs. Now we are going to see about PDPCOR. So after all this, we are going to end our program. So it has gone to some other program, that is this startup file programs. Now we can stop our exhibition. We cannot see the values changing on this PSOR, PCOR, PTOR because we have not connected any board to this PC. We are just simulating the program, so we cannot be able to see the changes on these registers. Now we are going to connect this board. Now I have connected this board to the PC, and I am going to show you how the LED is going to be blinked upon dumping this program. So I am going to show you the LED lighting up after dumping this program into this development board. I am going to dump this program now. We are going to rebuild this program. Now we can see the LEDs has turned to white color because of the three combinations of red, green and blue. We are going to see a white light here. Now we are going to debug this program so that we can see the step-by-step change of the state of LEDs. I am going to run this program to this point first. Now we can see the registers getting changed, and you can view here if you want to see something. And I am now driving a value of all F's into this port data direction register, and we all know that these LEDs are connected with the cathode at the port pin and anode to the ground, so that after framing this port D as output port, the default value being 0000 on all the port pins, the LEDs are going to be light up, and you can see the change now. We have got the LED color red and green combined to get some yellowish color, and we are going to write a 1 on the particular port pin so that it makes the LED off, and you can see the change. Now we have got red color LED, because the green has turned off because of writing 1 onto the particular port pin. Again this has gone off. Now there is no LED lighting here. Now we are doing the same with PCR1 of PD. And prior to making the port D as an output port, we are writing some data value 02, so that the particular port pin is made 1 and this LED does not light up after making this port pin as an output port. And you can see the change. Now after writing this value to this data direction register, the blue LED is not lighting up because we have written some value 02 at this instant. Now we are going to use the port clear register to clear those contents to light up the LED again. And you can see the blue LED has light up now. In the same way we are going to light up the rest LEDs. Now the color has got changed to pink color. Now it is in white color, meaning that all the 3 LEDs are in on state. Now the program has come to an end. Now we can stop this debugging session. And now I am going to show you the blinking of LEDs with some particular time delays in between them. I am going to disable all these statements and enable these statements which I have written earlier. So here I am using this port toggle register. I am writing some particular value to the port toggle register before and after delay, so that once it will be turned on and at the other instant it will get turned off. So I am writing the same value with the help of this store instruction at the same memory location with the same data, so that the data gets toggled after this particular delay. And a delay program can be called in two ways, that loading the delay address and moving it to PC, or directly calling the delay with the BL instruction, branch with link register instruction. So it comes to delay, takes the data of data 7 is 6 Fs, and it will decrement to 0, and whenever it becomes 0 it will come to the previous position where it was executing. BXLR is branch with exchange in the link register. Link register will be carrying the return address of this statement, and the execution starts from this statement after coming out of this loop. Now we are going to dump this program and we are going to see how the LED is going to be blink periodically. Now I am going to dump this program. You can see the LEDs getting blinked now. Blue, green, red, blue, green, and again it's coming back to red. So the view may not be good here, but we can observe the color changes in the LEDs. So with this I am going to stop this tutorial, and in the next tutorial we are going to see about ADC and DAC. Thank you for watching.